Imagine looking at the sky and finding a star that should not be there. A star so ancient that it shone even before the Earth, the Sun, or our galaxy existed. This is Earendel, the point of light at the end of the universe. But here is the suspense that is dividing the scientific community. The light that you are seeing now is from a star that already died 13 billion years ago. We are observing a cosmic ghost. And the mystery gets even deeper. New data from 2025 suggests that everything we thought we knew about Earendel may be a lie. Astronomers are now in a desperate race to discover if this world record is a real individual star, or if we have been deceived by a colossal optical illusion created by the universe's own gravity. If it is a star, it breaks the laws of physics regarding early stellar formation. If it is a cluster, it proves that the early universe was much more chaotic than we imagined. But there is a hidden detail in the James Webb data, a mysterious blink that could finally reveal the truth. Prepare to question your perception of time and space, because what we discovered about Earendel changes everything we know about our place in the cosmos. The Shores of the Cosmic Dawn, a prologue to deep time. The human quest to understand the cosmos is often described as an attempt to read a book where the first few chapters have been torn out. We reside on a tiny, fragile stage, a pale blue, suspended in a sunbeam, yet our curiosity compels us to look back across the vast, dark ocean of space-time toward the very beginning of everything. The discovery of WHL-0137, LS, an object colloquially known as Earendel, represents one of the most significant breakthroughs in this archaeological endeavor. It is a point of light that has traveled across the expanding tapestry of the universe for nearly 13 billion years to reach our mirrors, offering a glimpse into an epoch when the first stars were just beginning to breathe life into the void. To conceptualize the significance of Earendel, we must adopt what has been termed the cosmic perspective. As Carl Sagan famously noted, the size and age of the cosmos are beyond ordinary human understanding. We are lost somewhere between immensity and eternity on our tiny planetary home. Brian Cox further enriches this perspective by describing the early universe as a day without a yesterday, a period of transition from a hot, dense primordial state to the structured cosmos of stars and galaxies we see today. Earendel stands as a sentinel at the boundary of that transition. The discovery of Earendel was made possible through the Reionization Lensing Cluster Survey, RELIX, using the Hubble Space Telescope, with subsequent confirmation and deeper analysis provided by the James Webb Space Telescope, James Webb Space Telescope. At a redshift of 6.2, the light detected from Earendel was emitted a mere 900 million years after the Big Bang, during the critical era of reionization. Due to the metric expansion of space, Earendel's current comoving distance is approximately 28 billion light-years, making it the most distant stellar object ever identified. The object is visible only because of a lucky alignment with a massive foreground galaxy cluster, WHL-0137-08, which acts as a gravitational lens, magnifying the light by thousands of times. The naming of the star, derived from Old English for morning star, evokes the imagery of the first light rising over the cosmic horizon, a theme echoed in J.R.R. Tolkien's mythology. This report examines the technical, physical, and philosophical dimensions of Earendel. It explores the mechanics of gravitational lensing, the debates surrounding the object's identity as a single star or a cluster, and its potential as a member of the legendary population 3 generation of stars. By synthesizing data from both the Hubble and Webb telescopes, we can begin to reconstruct the history of this ancient beacon and its role in the grand narrative of the universe. The investigation into Earendel has followed a series of critical milestones, starting with its initial discovery on March 30, 2022, when the Hubble Space Telescope first identified the object at a redshift of 6.2. Subsequent color detection on August 8, 2023, using the James Webb Space Telescope's NIRCam confirmed its B-type star characteristics, while more recent spectroscopic analysis on July 31, 2025, provided a precise redshift of 5.926 and introduced the cluster hypothesis. Additionally, theoretical models from late 2024 have focused on the effects of dark matter subhalos on magnification limits to better understand the object's nature. The importance of Earendel cannot be overstated, as it serves as a bridge between the mathematical abstractions of the Big Bang and the physical reality of our world. It has pushed the boundaries of observational astronomy, allowing us to peer into the first billion years of existence and witness the dawn of stellar physics. This era, known as the Cosmic Dawn, is when the first light began to permeate the universe, ending the cosmic dark ages and initiating the process of reionization. Earendel is not just a point of light, it is a direct witness to the end of that darkness. As the James Webb Space Telescope continues to analyze its spectrum, we are not just collecting numbers. we are reading the first chapter of the story of light in the universe. The mechanism of the heavens, gravitational lensing, and the WHL0137-08 cluster. The visibility of an individual star across such a staggering distance is fundamentally impossible with current technology under normal circumstances. Even the most luminous stars are typically lost in the collective glow of their host galaxies when viewed from billions of light-years away. Earendel's detection is a triumph of natural magnification through the phenomenon of gravitational lensing. This effect, a direct consequence of Einstein's general relativity, occurs when the mass of a foreground object, in this case, the galaxy cluster WHL0137-08, warps the surrounding spacetime, bending and focusing the light from background sources. The foreground cluster WHL0137-08 is a massive collection of galaxies bound together by gravity. Its immense mass creates a wrinkle, or ripple, in the fabric of spacetime known as a caustic. Sunlight hitting the uneven surface of the water in a swimming pool is bent and focused into bright, wavering lines or filaments on the pool's floor. In the cosmic version of this analogy, the cluster mass is the water's surface, and the distant light from Earendel is the sunlight. When a background object aligns perfectly with a caustic ripple, its brightness can be magnified by factors exceeding 1,000 or even 40,000.1. The physics of this phenomenon involves both convergence, which describes the general magnification of the background area, and shear, which describes the stretching of the image into an arc. The functional impact of these lensing features on Earendel is significant, as the foreground galaxy cluster WHL0137-08 at a redshift of 0.566 warps spacetime to act as a magnifying glass, while the caustic line amplifies the light beyond the detection threshold. The host sunrise arc galaxy is distorted into a crescent shape, and mirror imaging from gravitational distortion produces duplicate images of clusters within that galaxy, while microlensing from substructures in the lens causes specific fluctuations in brightness over time. The alignment required for this is so precise that Earendel must be physically tiny, less than 0.3 parsecs across, to appear so sharp and remain so close to the caustic line, reinforcing the idea that it is an individual star or binary system rather than a diffuse cluster. The cluster WHL0137-08 acts as a colossal magnifying glass in the sky, focusing the light from the sunrise arc into our view. This cluster is dominated by dark matter, which accounts for approximately 85% of its total mass. The distribution of this dark matter is critical. While large-scale models provide a smooth lensing potential, smaller subhalos of dark matter can perturb the caustic line, creating a corrugated effect. These subhalos are optically invisible but can have a pronounced effect on the lensing strength, potentially relaxing the size constraints for Earendel and allowing a star cluster to mimic the appearance of a single star. The tapestry of space, redshift, expansion, and the barrier, the concept of distance in an expanding universe, is a multifaceted metric that challenges our intuitive understanding of space and time. When astronomers state that Earendel is the most distant star, they are referring to its redshift, a measure of how much the light from the object has been stretched by the expansion of space during its journey to Earth. Earendel's redshift is measured at 6.2, which corresponds to a light travel time of 12.9 billion years. This means we see Earendel as it existed when the universe was only about 900 million years old, roughly 7% of its current age. The physics of redshift in this context is cosmological, not a standard Doppler effect. While Doppler redshift occurs when an object moves through space, cosmological redshift occurs because space itself is expanding, carrying the galaxies along with it. Specific redshift parameters highlight Earendel's status, as its redshift of 6.2 places it in the era when the universe was only 900 million years old during the cosmic dawn. The expansion factor of 7.2 has stretched its ultraviolet and visible light into the infrared spectrum, which means that while the light travel time is 12.9 billion years, the current comoving distance of Earendel's remnants is approximately 28 billion light-years. As light travels across billions of light-years, its wavelength increases in direct proportion to the expansion of the universe. At this redshift, light emitted by Earendel in the ultraviolet and visible spectrum has been stretched by a factor of 7.2, shifting it deep into the infrared. This fundamental shift is why the James Webb Space Telescope, with its infrared-optimized detectors, is the only instrument capable of resolving Earendel's true temperature and composition. This expansion also creates a distinction between look-back distance and comoving distance. While the light traveled for 12.9 billion years, the universe continued to expand throughout that journey. Consequently, the physical location where Earendel resides today is far beyond the initial emission point. As Neil deGrasse Tyson and other science communicators note, the further away we look, the the further back in time we see, allowing us to witness the continuous unfolding of cosmic evolution. Anatomy of the morning star, B-type physics and massive stellar evolution based on data from the James Webb Space Telescope's near-infrared camera, NIRCam. Earendel has been identified as a massive B-type star. B-type stars are among the hottest and most luminous objects in the universe. They are typically blue or blue-white and are characterized by intense radiation and strong stellar winds. The spectral analysis indicates that Earendel is more than twice as hot as our Sun and roughly 1,000,000 times more luminous. If Earendel is an individual star, its surface temperature is estimated between 13,000 K and 16,000 K, which places it firmly in the main sequence phase of hydrogen burning. However, its mass is estimated to be between 50 and 200 times that of the Sun, making it a true stellar giant. The physical properties of Earendel, when estimated as a single star, stand in stark contrast to our Sun. Earendel is a B-type star with a temperature between 13,000 and 16,000 K, whereas the Sun is a G-type star at 5,778 K. Earendel's luminosity ranges from 1 million to over 3 million times that of the Sun, and its mass is estimated between 20 and 200 solar masses. With a radius between 103 and 393 times that of the Sun, its lifespan is only roughly 1 to 5 million years, compared to the Sun's 10 billion years. Stellar evolution for such massive objects follows a live fast, die young scenario. While a star like the Sun can burn its fuel for billions of years, a star with Earendel's mass will exhaust its core hydrogen in just a few million years. Given that Earendel existed 12.9 billion years ago, it is an inescapable fact that the star has long since exploded as a supernova and likely collapsed into a black hole or a neutron star. We are observing the ghost of a star that vanished eons before the Earth even formed. The extreme brightness of Earendel is only possible because of its position along a wrinkle in space-time that provides extreme magnification. The Sunrise Arc, a galaxy distorted by time and gravity. Earendel is not an isolated wanderer. It is a resident of a distant galaxy officially designated WHL0137, ZD1, and nicknamed the Sunrise Arc. This galaxy is a prime example of the chaotic and turbulent nature of the early universe. Because of the gravitational lensing by the WHL0137-08 cluster, the galaxy's light is distorted into a long, thin, crescent-shaped smear that stretches across the sky, with an angular size exceeding 15 arcseconds. This arc provides a rare opportunity for astronomers to study the internal structure of a galaxy from the first billion years of cosmic history. The Sunrise Arc is the most strongly magnified galaxy known from this era, allowing us to see details as small as parsec-scale star clusters. The architecture of the Sunrise Arc reveals distinct features that characterize the early universe. Its star-forming regions appear as clumps of intense light estimated to be less than 5 million years old, while Cluster 1b is an older, more established star cluster between 30 and 150 million years of age. The host galaxy itself sits at a spectroscopic redshift of 5.926 and features caustic symmetries where mirrored images across the ripple show identical properties. Observations from the James Webb Space Telescope have revealed 7 distinct star-forming clumps and regions where star formation occurs at exceptionally high densities. These features are mirrored on either side of the caustic line, a direct result of the lensing geometry. The galaxy is expected to be metal-poor, lacking the heavy elements produced by multiple successive generations of stars. This pristine chemical environment is crucial for understanding the transition from the Big Bang to the complex chemistry of the present day. The Sunrise Arc serves as a laboratory for observing this chemical enrichment in its infancy, providing baby photos of structures that would eventually evolve into massive galaxies. Recent simulations, such as the SIEGE project, demonstrate that such compact star clusters naturally form in the early universe when sub-parsec physics and stellar feedback are included. The shadow and the light, the binary hypothesis in companion stars. One of the most intriguing aspects of Earendel is the possibility that it is not a single star, but part of a binary system. In the local universe, the majority of massive O and B-type stars are found with at least one companion. Detecting such a companion at a distance of 12.9 billion light-years is an immense challenge, as even under extreme magnification, the two stars would be indistinguishable as separate points of light on the sky. However, spectral energy distribution data from the James Webb Space Telescope has provided subtle hints of a second star. The light detected from Earendel shows a spectral signature that is difficult to explain with a single temperature model, exhibiting a strong Balmer break alongside a blue UV slope. This discrepancy has led some researchers to propose a binary model where Earendel consists of two distinct components. In this scenario, a hot primary star with a temperature of roughly 34,000 K and a radius of 23 solar radii drives the UV slope and high luminosity, while a cool companion at 9,000 K with a much larger radius of 184 solar radii explains the longer wavelength colors. The implications of a binary system are profound because while the massive primary star would have exploded as a supernova within a few million years, the smaller companion could potentially live for billions of years. This means that while Earendel is a cosmic ghost, its partner might still be shining today. Drifting through the modern descendant of the sunrise-arc binary interactions can also trigger mass transfer or mergers, potentially creating stars that are even more luminous than their mass would normally allow, which might explain how Earendel became bright enough to be visible. The Great Schism, star or cluster? The 2025 controversy in mid-2025, a new study challenged the established narrative that Earendel is an individual star, suggesting it may actually be a tightly bound star cluster. This controversy highlights the extreme difficulty of interpreting data at the very edges of the observable universe. The argument for the cluster hypothesis is based on spectral matching, as researchers compared Earendel's light to a known star cluster in the sunrise arc called 1b, and found that both share nearly identical characteristics. Both are metal-poor, share similar ages between 30 and 150 million years, and exhibit high stellar surface densities. The debate between the individual star and star cluster hypotheses is supported by different sets of evidence. Those favoring the individual star model point to Earendel's position on the caustic ripple, its small size constraint of less than 0.3 parsecs, and its sharp appearance as a persistent point source. Conversely, the cluster hypothesis relies on spectral similarities to cluster 1b and the fact that the light fits simple stellar population models. Furthermore, recent reevaluations of magnification suggest that if the factor is as low as 43 to 67, a single star would be too faint to be seen, requiring a cluster instead. The crux of the debate lies in the magnification model, where previous estimates exhibited significant uncertainty ranging from 4,000 to 35,000.11, accounting for invisible mini-halos of dark matter could relax the size constraint by up to tenfold, making the object's dimensions compatible with a compact star cluster. Population 3. The quest for primordial purity and the first light. One of the most profound hopes for the Earendel discovery is that it might provide the first direct evidence for population 3 stars. These are the hypothesized first generation of stars that form from the pure hydrogen and helium left over from the Big Bang, before any heavier elements existed. Population 3 stars are the holy grail of observational cosmology because they were the primary engines of reionization and the source of the first heavy elements. These stars are distinguished from modern generations by their metal content and mass. Population 1 stars like our Sun have high metallicity, while population 2 stars have low metal content. In contrast, population 3 stars possessed zero metallicity and were likely extremely massive hypergiants. While the probability of Earendel being a pure population 3 star is considered small, it exists at exactly the right time and environment to be a strong candidate or a direct descendant. Key factors in the population 3 investigation include spectral signatures, where a pure population 3 star would show no evidence of elements like carbon or oxygen. Earendel's estimated mass between 50 and 200 solar masses is consistent with the lower end of the predicted range for these primordial giants. Its discovery has opened a new realm of the universe to stellar physics, allowing us to probe individual stellar systems from the first billion years. Recent simulations suggest that population 3 formation could have continued in low-mass halos until the end of reionization, meaning Earendel's host galaxy could still have been harboring these ancient stars. The pool of spacetime, caustics, microlensing, and optical illusions. The physics of Earendel's visibility is intimately tied to the geometry of the caustic ripple, a line of theoretically infinite magnification in a gravitational lens. Earendel appears as a single point because it is positioned almost exactly on the caustic line itself, providing the magnification factor that allows it to emerge from the host galaxy. However, this magnification is subject to the influence of microlenses, small, dense objects within the foreground cluster, such as stars or planets. Microlensing can cause a distant star to flicker or fluctuate in brightness over months or years, which serves as a diagnostic tool. A single star would show rapid, sharp blinks as it crosses microcaustics, while a cluster would show a steady output. Specific lensing phenomena each have distinct causes and effects on Earendel. Macrolensing from the cluster WHL0137-08 stretches the galaxy into the sunrise arc, while caustic alignment provides the extreme magnification needed for detection. Microlensing from intra-cluster stars or planets is predicted to create brightness flickers, whereas millilensing from dark matter subhalos can cause positional shifts or distorted arcs. The shimmering pool analogy captures this structure, where Earendel is a bright point created by the bending of light. If Earendel is indeed a single star, its light curve would eventually reveal its nature through these flickers. Furthermore, different dark matter models predict specific asymmetries that could be tested by observing the spatial distribution of transients like Earendel. Benchmarking the void, Earendel and the hierarchy of cosmic records. To appreciate the scale of Earendel's discovery, it is helpful to compare it with other record-breaking celestial objects. Earendel represents a massive leap forward, as the gap between the previous record holder, Icarus at a redshift of 1.5, and Earendel at 6.2 spans nearly 3.5 billion years of history. In the hierarchy of cosmic records, Earendel is the farthest individually seen star candidate at a comoving distance of 28 billion light-years. It surpasses Icarus, which has a comoving distance of 14.4 billion light-years, and Quiller, a lensed red giant at a redshift of 3.3. For further context, the farthest galaxy pre-James Webb Space Telescope was GNZ11 at a redshift of 10.6, while recent observations have identified stars in MOMZ14 at an incredible redshift of 14.44. Earendel takes us into a regime where the physics of stars was fundamentally different, shaped by a universe that was smaller, hotter, and chemically pristine. It is also important to distinguish Earendel from the Methuselah star, which is an ancient survivor located in our own galaxy. In contrast, Earendel is a star we see exactly as it was billions of years ago. This direct view of the early universe as it was happening is what makes Earendel a unique find. Recent discoveries of other strongly lensed supernovae and star clusters collectively confirm that we have entered a new era of caustic crossing astronomy, where individual stellar lives can be studied across more than 12 billion years. The ghostly sentinel, temporal displacement, and the archaeology of light, the light we receive from Earendel, is a profound philosophical challenge to our perception of time. Because light travels at a finite speed, we are never seeing the universe as it is now, but as it was when the light was emitted. This archaeology of light becomes extreme for Earendel, as 12.9 billion years ago it emitted the photons we see today. Only a few million years later, it exploded as a supernova, meaning it has been dead for nearly 13 billion years while its photons were still traveling through space. The temporal journey of Earendel's light follows a massive timeline, beginning with photon emission 12.9 billion years ago during the Era of Reionization. Roughly 12.89 billion years ago, the star collapsed as a supernova, vanishing long before the Earth existed. About 4 billion years ago, that light passed through the lens cluster WHL0137-08, being bent and magnified before finally being captured by Hubble and Webb detectors between 2022 and 2023. In our current reality, Earendel likely exists as a black hole 28 billion light-years away. As Carl Sagan noted, we are star stuff, contemplating the stars. But we are also time travelers, reconstructing our history through the light of these ancient giants. The nitrogen in our DNA and the iron in our blood were forged in the hearts of stars like Earendel, making this distant point of light a direct link to our own biological origins. Conclusion: a reflective synthesis of the morning star Earendel, the morning star at the edge of the observable universe, serves as a bridge between the mathematical abstractions of the Big Bang and the physical reality of our world. Whether it is ultimately confirmed as a single massive star, a binary system, or a dense cluster of globular cluster progenitors, its significance remains undiminished. It has pushed the boundaries of observational astronomy to a redshift of 6.2, allowing us to peer into the first billion years of existence and witness the dawn of stellar physics. The discovery highlights the extraordinary synergy between human ingenuity and the natural geometry of the cosmos. By using the massive WHL0137-08 cluster as a gravitational lens, we have turned the universe's own mass into a tool for discovery, proving Einstein's theories across nearly 13 billion years of space and time. In the final analysis, Earendel is a humbling reminder of our place in the cosmic ocean. We are a young and curious species, yet we have developed the capacity to find a single point of light from the beginning of time. Earendel stands as a testament to our ongoing quest to read the first chapters of the cosmic book, reminding us that we are part of a vast narrative that began billions of years before we ever opened our eyes to the stars. As we continue to monitor the mystery blink and analyze the spectra of these ancient beacons, we are uncovering the very foundations of our own existence in the great cosmic dark.